Bismillah ar-Rahman ar-Rahim. Welcome to lecture number 21 for CS 311 Theory of Automata. We will start the topic conversions between FA, TG and regular expression. We have already discussed these three concepts: finite automata, transition graph and regular expression. And now we will see that we can make conversion between these three. It means we can convert FA to transition graph and vice versa. We can convert transition graph to regular expression and vice versa. And we can make transition between FA and regular expression. So this is the discussion agenda. We will revise our previous lecture and we will start Klein's theorem, which basically discusses the conversion between FA, transition graph and regular expression. Okay, so let's revise our previous lecture. In previous lecture we discussed GTG, or generalized transition graph, and this was the definition of GTG. When there are finite number of states, at least one is start state and some, maybe none, final states. Here it's important to pay attention to this at least one. It means there may be more than one start states. Then finite set of input letters, and then directed edges connected some pair of states labeled with regular expression. And it's actually not a relaxation but a restriction. So we have seen some examples of GTG. This was one example. Define GTG for language L of strings containing double A or double B. So this was the regular expression and this was its corresponding GTG. So this one is labeled this one, and then A plus B star is labeled with this one, and this A plus B star is labeled here. So you see it's much more simpler than a finite automata. So it gives us more freedom to write languages. This was another example. Language L of strings beginning with and ending in same letters. So this is beginning with A, ending in A, beginning with B, ending with B. Similarly, single A and single B are also strings that begin and end at the same letter. So this was its corresponding GTG. This is for single A and for single B, and this is language that begin with A and ending with A. Similarly, language begin with B and ending with B. This is just one GTG. You can make it more simpler than this one. You remember that for one language there may exist multiple GTGs. This was another example, beginning and ending in different letters. So beginning with A, ending with B, beginning with B, ending with A. So this is one, beginning with B, ending with A, beginning with A, ending with B. It's a simple GTG. So a language L may be accepted by the following GTG as well. This is another GTG that accepts the same language. So this is another example having triple A or triple B. So this is its corresponding GTG that we have discussed, or this one. So GTG has non-determinism. So transition graph and GTGs provide certain relaxation. One relaxation is there may exist more than one path for a certain string, or there may not be any path for a certain string. This property creates non-determinism, and it can also help us in differentiating transition graphs or GTGs from FAs. In FAs, there is no non-determinism. This program is always deterministic. So FA is also called deterministic finite automata or DFA. Okay, so let's start today's lecture. It's about Kleen's theorem. And it basically says that if a language can be expressed by FA or transition graph or regular expression, then it can also be expressed by the other two as well. So what it basically says, if a language can be expressed by FA, then it can be expressed by transition graph, and it can also be expressed by regular expression. Similarly, if a language is expressed by transition graph, it can be expressed by FA and it can be expressed by regular expression. Or, if a language is expressed by regular expression, then it can be expressed by a transition graph and it can also be expressed by corresponding FA. So it's actually talk about the conversion between these three types. So the theorem is proved by proving the following three parts. So part 1 is, if a language can be accepted by FA, then it can be accepted by transition graph as well. Part 2 can be, if a language can be accepted by transition graph, then it can be expressed by regular expression as well. And part 3 is, if a language can be expressed by regular expression, then it can be accepted by FA as well. So if we prove these three parts of Kleen's theorem, we basically prove the conversion from FA to TG and TG to regular expression and regular expression to TG and regular expression to FA. So it actually shows the conversion between these three types. Let's start from Kleen's theorem part 1. So by definition, every FA can be considered to be a transition graph as well. Therefore, there is nothing to prove. You remember in transition graph, there are certain relaxations. One relaxation is there may exist multiple beginning states. Now, it's not necessary that there are multiple start states in transition graph. There exists one, at least one, but there may be more. So if we do not use more than one beginning state, we basically have FA. Another relaxation is there may exist multiple paths for a transition, or there may not exist any path for a transition in transition graph. So if we actually do not use these relaxation, we may have an FA. And in transition graph, the strings may be labeled by substrings. So again, it's a relaxation. If we do not use this relaxation, we have basically an FA. So actually, every FA is considered as a transition graph. So therefore, we don't need to prove anything, and this theorem is actually done. Let's go to part 2. And the statement of this part 2 is, if a language can be accepted by a transition graph, then it can be expressed by regular expression. So what actually we are doing, we are going to show the conversion between transition graph to regular expression. So there are different steps that are involved in this conversion. Step number 1, create a unique uninterable minor state and a unique unleavable plus state. So let's say we have this transition graph. This is two initial states. One is this one and one is this. Another is two plus state. One this one this one. So what we do, we create a uninterable minor state. So we basically create a minor state here, and we connect them by lambda, and we basically create one unleavable plus state, and we connect these plus state by lambda. Remember, by doing so we need to remove the minus states from here and the plus states from here. These are no longer plus state. So what we did, basically we converted transition graph to GTG. Remember, in transition graph we did not talk about lambda transitions, but in GTG we have lambda transition, so it's actually GTG. Step number 2, bypass and state elimination. Now one by one, in any order, bypass and eliminate all the non-minus and non-plus states in the edge. The label of each resultant edge is the concatenation of the label on the incoming edge with the label on the loop edge if there is one, and the label on the outgoing edge. Let's see. So we have non-final state 4, 5 and 6. Now we want to eliminate this state number 5. Now there is this incoming transition, a loop and outgoing transition. So we basically remove state number 5 like this, and we concatenate these labels on the edges of incoming, loop and outgoing. So incoming edges are 2, loop is R3 star, and R4 is this one. So this basically one elimination or bypass state. Using this technique we will eliminate states one by one, and eventually we will remove all the non-final and non-initial states. This is another example. Consider the part of a TG containing a circuit at a state is shown below. Now this is not one straightforward, because we have one transition as this one and another transition is let's see, like this and this. So basically if we remove state number 3, we have to deal with these loops. So first is we eliminate state number 3 and we get R1, R2 star because of this loop, and R3, this one, and then we have R4. So from state 4 to state 3 there is a loop which is R4, R2 star and R3. So you have to be very careful when you eliminate states, because eliminating states may involve multiple paths that you have to make sure that the resultant transition graph follow these paths. Step number 3. When two states are joined by more than one edge going in the same direction, unifying them by adding their labels. So for example, R4 and R5, they are labeled by two transitions. So what we can do, we can reduce it to R1 plus R2. Similarly, there is R3 and R4. So we can have R3 plus R4. Step 3 can be generalized to any finite number of transitions as well. So let's say we have R1, R2, Rn. So we can combine them by R1, R2 up to Rn. Finally, when all that is left is one edge from initial to final, the label on that edge is a regular expression that generates the same language as was recognized by the original machine. Let's see an example. We have this example of transition graph, and what we do, we have to create its regular expression. So there is one initial state, two final state, and there are many labels in the middle, and we will see how to convert GTG to regular expression. Now let's follow step number 1. In step number 1, we create a unique initial state and a unique final state. So there is one initial state, so no need to convert anything, and we create one final state and we connect them by lambda transition, and we also converted these labels to regular expression, because what we do, we convert TG to GTG, and in GTG labels are transitions are labeled with regular expression. Now you remember there was step number 4 that says that if we have multiple paths, so you remember this is one path and this is another path, and we basically can remove this 2 by labeling this transition as AA lambda and BB lambda, and we can basically combine this into one path by adding a plus in between. So we have AA lambda plus BB lambda. Basically we can remove this lambda because a string concatenated with lambda is that string. So it's actually AA plus BB. Now let's try to remove this state. State number 1. So we have this label as a loop, and this label. So this label double A plus double B, this label as a loop a plus b whole star and double a plus double b at the end, and we have one initial state and one final state. So basically this is our regular expression. So hence the required regular expression is double a plus double b, a plus b whole star, double a plus double b, which means begin and end with double letters. This is the definition of the language. So in this example, we see how to convert a transition graph to regular expression. Now, it's better that you practice on this step, on this clean closure part 2 as a quiz. So I give you the example transition graph for even language, which is given as this one. There is one initial and one final. So it will be a bit tricky, but what you do, you create its corresponding regular expression using Kleen's theorem part 2. And by practicing in this example, you will learn how to convert transition graph to regular expression. So okay, so let's start Kleen's theorem part 3. If a language can be expressed by regular expression, then there exists an FA accepting the language. So every regular expression can be built from the letters of the alphabet and lambda by repeated application of certain rules, addition, concatenation, and closure. This is the property of regular expression that we have studied before. So while building the regular expression, sometimes the corresponding FA may be built easily. So there are certain rules in this part 3. So if there is an FA that accepts any particular letter of the alphabet, there is an FA that accepts only the word lambda. And if there is FA that accepts regular expression R1 and there is FA that accepts regular expression R2, then there is an FA that accepts the language defined by the concatenation of two regular expressions. Similarly, there is R4, there is FA that accepts regular expression R1, and there is an FA that accepts regular expression R2. Then there is an FA that accepts the language of the concatenation of two strings. Similarly, if there is an FA that accepts regular expression R, then there is an FA that accepts the language defined by R star. So these are the rules in part 3, and you will see that we can build corresponding FA easily. So the language L consisting of only string B, we can build FA like this. This accepts the language B. Consisting only lambda, we can build its FA like this, plus minus as a one state, and the rest of the things are accepted like this. Actually, they are not accepted, they just stay in the dead end state. Only lambda is accepted. Rule number 3. Using the FA corresponding to R1 and R2 can be both corresponding to R1 plus R2. Let's take an example. So let's say we have one regular expression R1 that define L1, and the corresponding FA is this. So it's A plus B whole star followed by B. It means strings ending at B. And this shows strings ending in B. And another regular expression that contain double A. So this is double A. Okay, so these are the two corresponding FAs that we have seen here. I have listed it here. Now we want to combine these two FAs. So here we have Z1. Z1 is initial state, which means initial state of this FA and initial state of this FA. Now new state after reading A or B. So in X1, if we read A, we go to X1. And in Y1, if we read A, we go to Y2, which is equal to Z2. And in X1 reading B, we go to X2. And in Y1 reading B, we go to Y1. This is different than this one, so let's give it name Z3. Now let's take Z2, which is X1, Y2. In X1 reading A, we go to X1, and in Y2 reading A, we go to Y3. Is different than these, so let's give it name Z4. In X1 reading B, we go to X2, and in Y2 reading B, we go to Y1. And it's actually this one, so we give it name Z3. Now let's take this Z3, which is basically X2, Y1, and since X2 is a final state, so we label it as plus. Now in X2 reading A, we go to X1, and in Y1 reading A, we go to Y2, which is Z2, and in X2 reading B, we go to X2, and in Y1 reading B, we go to Y1, which is actually Z3. Now this is the new one, so we take Z4, which is basically X1, Y3. In X1 reading A, we go to X1, and in Y3 reading A, we go to Y3, which is basically same as Z4. In X1 reading B, we go to X2, and in Y3 reading B, we go to Y3, which is a new state, so let's call it Z5. Now in X2 reading A, we go to X1, and in Y3 reading A, we go to Y3, so basically it is Z4. In X2 reading B, we go to X2, and in Y3 reading B, we go to Y3, which is same as Z5. So actually we do not have any more new states, so we stop here. Our FA is basically this new FA, and if we build the corresponding FA, it will look like this. So now we have Z1 initial state, reading A we go to Z2, reading B we go to Z3, Z3 is final, Z2 reading A we go to Z4, reading B we go to Z3. Now Z3 reading A we go to Z2, reading B we go to Z3, Z3. Z4 reading A, we go to Z4. Reading B, we go to Z5. Z5 reading A, we go to Z4. Reading B, we go to Z5. So this is our new FA, which is actually the addition of two FAs. One FA that ends at B and the second FA that contains double A. So this FA basically ends at B and or it contains double A. Now I will give you another quiz. We have R1 and R2 and their corresponding FAs are given, and what you have to do, you have to combine these two FAs, so you have FA for R1 plus R2. I think we should stop it here.